The Indian Ocean is the third largest ocean on the planet. It connects Africa, Asia, and Australia. More than 1 billion people live along its shores. Ships have crossed it for thousands of years, and somehow it is still one of the least understood bodies of water on Earth. More of the surface of Mars has been mapped in detail than parts of the Indian Ocean's deep floor. What little has been observed below the first kilometer has come back piece by piece from isolated expeditions, and what those expeditions found has consistently surprised the people running them. There is life down there that runs on chemistry instead of sunlight. There are ridge systems and volcanic chains that were still being named within the last few decades. There are features on the seafloor that scientists are still trying to explain. And there is the island of Mauritius, a small 9 million-year-old volcanic island sitting quietly in the middle of the ocean, whose beaches contain minerals that are nearly 3 billion years old. Those minerals could not have formed on Mauritius. The island is far too young. They came from something older, something that once sat above the waterline and no longer does. Scientists have given it a name, Marishia, a lost continent, roughly the size of Greenland, before it broke apart, now buried beneath the floor of the Indian Ocean, discovered not through a deep-sea drill or a submersible, but through grains of sand on a beach. The Indian Ocean holds a gravity hole, a lost continent, and ecosystems that no textbook anticipated. Tonight, we go through them, one by one, carefully, without rushing. Before we go any further, if you're new here, subscribe. There's a lot more where this came from. So get comfortable. This one goes deep. Across maps that once guided sailors between continents, the Indian Ocean often appeared as an open passage rather than a destination in itself. Trade winds carried vessels along its surface, linking distant coasts, yet the vast water between those routes remained largely unexamined. Attention settled on movement above, while the depths below stayed quiet, unmeasured, and patient. Even as global exploration advanced, this ocean received a different kind of gaze. Other regions drew sustained focus, shaped by patterns of research, proximity to powerful institutions, and the practical ease of repeated access. In contrast, much of the Indian Ocean stretches far from major research hubs, where reaching the deep seafloor requires long voyages across isolated water. Each journey demands time, coordination, and considerable expense, limiting how often scientists can return to the same place. The challenge is not only distance, but the nature of the seabed itself. Large portions lie beneath layers of water so deep that even modern instruments must work at the edge of their limits. Equipment must endure immense pressure, operate without direct human presence, and relay information through a column of water that resists clarity. Small technical failures can end an expedition's progress, turning months of preparation into fragments of data. For much of scientific history, understanding here did not grow steadily. Instead, it accumulated in pieces. A research vessel might pass through a region once, gather samples or measurements, and then move on, leaving behind a narrow glimpse of a much larger landscape. Years could pass before another expedition returned, often with different tools, different priorities, and different questions. What formed was not a continuous map, but a mosaic assembled slowly from scattered contributions. This pattern shaped the way knowledge developed. In places where repeated surveys refine details, science often moves toward precision, smoothing uncertainties into clearer outlines. In the Indian Ocean, many areas remained at an earlier stage, where even broad features were still being outlined. The difference is subtle but important. It means that discovery here does not always arrive as a small adjustment to what is already known. It can appear instead as something newly revealed, not because it formed suddenly, but because no one had yet seen it in full. There is a quiet imbalance in how oceans are perceived. The size of a place does not guarantee the depth of understanding attached to it. Though this ocean ranks third in global scale, its deeper regions have often lived outside the central narratives of exploration. The absence of constant attention allowed large portions to remain open, waiting for the slow arrival of instruments capable of reaching them. As technology improved, glimpses began to connect, but the sense of incompleteness never fully disappeared. Even now, certain stretches are known more by inference than by direct observation, their shapes and compositions suggested through indirect measurements rather than detailed surveys. Scientists working here often begin with foundational questions, establishing what exists before exploring how it behaves. Because of this, each new expedition carries a particular weight. It is not only adding detail, but sometimes building the first clear outline of a place that has long remained indistinct. What emerges can feel abrupt, as if the ocean is revealing something unexpected, when in truth, it has simply been waiting beyond the limits of prior reach. In this way, the Indian Ocean holds on to a different rhythm of discovery, one shaped by distance, difficulty, and the long gaps between careful observations. Far below the surface roots that once defined this ocean, the ground does not settle into stillness. It rises, folds, and stretches into forms that resemble a buried geography, one that no horizon reveals. The impression of a smooth, endless floor fades quickly when traced with instruments that listen rather than see, mapping depth through echoes that return with quiet precision. What appears at first as uniform darkness resolves into separate regions, each with its own shape and character. The central Indian Basin spreads wide and deep, a broad depression holding layers of accumulated material. Nearby, the Wharton Basin extends with a different contour, its boundaries shaped by forces that have shifted over immense spans of time. To the northwest, the Arabian Basin rests within its own frame, while the Somali Basin curves along another margin, influenced by distant continental edges. Farther south, the Crozet Basin forms yet another distinct domain, separated not by visible walls, but by subtle changes in elevation that guide currents and sediments across the seabed. Between these basins, ridges rise like long submerged divides. They are not abrupt cliffs, but gradual uplifts, stretching across great distances, sometimes linking regions, sometimes separating them. Their presence alters how material settles, how heat moves through the crust, and how water flows in slow, unseen patterns. In some places, these ridges interrupt the descent of particles drifting down from above, causing sediments to gather more thickly on one side, while leaving the other more exposed. The arrangement of these features shapes the distribution of energy beneath the ocean. Heat emerging from within the planet does not escape evenly, but follows pathways influenced by fractures and elevations in the crust. Some areas release it more readily, while others remain comparatively still. This uneven exchange creates subtle gradients, influencing chemical conditions that differ from one basin to the next. Sediment follows its own quiet logic. Fine particles travel through the water column before settling, guided by currents that shift direction over long distances. In deeper basins, these particles accumulate slowly, forming layers that record passing ages. Along elevated regions, the same material may be swept aside, leaving harder surfaces uncovered. Over time, this contrast builds a patchwork of soft plains and firmer ground, each supporting different forms of life. Organisms that inhabit these depths respond to this hidden structure. Some require stable surfaces where they can anchor. Others depend on the steady fall of organic matter that collects in lower regions. The availability of nutrients, the presence of mineral rich areas, and the subtle variations in temperature all trace back to the shape of the seafloor itself. Life here does not spread evenly, but follows the contours carved by geology. The idea of a single featureless abyss gives way to something more intricate. Each basin becomes a quiet world, defined by its depth, its sediments, and its connection to surrounding features. Ridges act as boundaries and bridges at once, influencing movement without ever being seen directly. As understanding of these forms grows, the sense of discovery shifts. Unusual findings no longer appear isolated, but linked to the underlying structure that makes them possible. The variations in the seafloor create conditions that differ from one region to another, allowing distinct processes to unfold side by side. In this layered landscape, the strangeness associated with the Indian Ocean begins to take shape not as isolated events, but as outcomes of a complex foundation where form and process remain quietly intertwined. There are places beneath the Indian Ocean where the crust itself is slowly opening, not with violence, but with a steady, almost imperceptible separation. Along these zones, the planet reshapes its outer layer in silence, creating lines that stretch for thousands of kilometers, unseen yet continuous, threading through the depths like the spine of something ancient. These are the mid-ocean ridges, vast volcanic systems that mark the boundaries between drifting tectonic plates. Instead of a single peak or isolated formation, they form extended chains rising from the surrounding seafloor with a quiet persistence. Their slopes are uneven, their crests fractured, and their presence alters the structure of everything around them. What might seem distant and disconnected at the surface becomes part of a continuous geological system below, linking regions through processes that unfold over immense spans of time. As plates move apart along these ridges, molten material from beneath the crust ascends to fill the space between them. It cools as it meets the surrounding water, solidifying into new rock that becomes part of the ocean floor. This process does not happen all at once, but in a gradual sequence, layer forming upon layer, extending the seabed outward in both directions. The ocean floor, in this sense, is not fixed, but quietly growing. The surface of these ridges carries the marks of this ongoing formation. Long fissures and cracks run along their length, some shallow, others reaching deeper into the crust. Through these openings, seawater begins a slow descent. It seeps downward, drawn by pressure and guided by the structure of the rock, moving into regions where heat from the Earth's interior becomes more intense. As the water travels deeper, its temperature rises. It interacts with the surrounding minerals, dissolving elements, and undergoing chemical changes that transform its composition. By the time it begins to move upward again, it is no longer the same water that entered from above. It carries with it heat and dissolved material, shaped by its passage through the crust. This circulation forms a continuous exchange between ocean and earth, one that remains hidden from direct view. The water emerges again through vents and fractures, releasing its contents back into the surrounding environment. These movements are not isolated events, but part of a larger system, repeating across different sections of the ridge network. The scale of these mountain chains becomes clearer when traced across maps of the seafloor. They extend across entire ocean basins, connecting distant regions through shared geological activity. In the Indian Ocean, several such ridges intersect and diverge, forming a network that reflects the shifting arrangement of tectonic plates. Their paths are not straight, but shaped by the motion of the Earth's outer shell, bending and branching over time. Where these ridges rise, they influence more than just the structure of the crust. They create conditions that differ from surrounding areas, affecting how heat is distributed and how chemical exchanges occur. These differences, subtle at first, become significant when viewed over longer periods, shaping the environment in ways that are not immediately visible. It is within this setting that some of the most unusual observations begin to take form. The ridges provide the framework, the fractures allow movement, and the interaction between water and rock creates possibilities that do not exist elsewhere. The landscape beneath the Indian Ocean is not only shaped by these processes, but animated by them, forming a system where change is constant, though rarely seen. At a certain point in the early 2000s, fragments of the deep began to take visible form, not through imagination, but through images carried upward from a place that had remained beyond sight. For the first time, scenes from the Indian Ocean's hidden interior reached a wider audience, offering a quiet but unmistakable shift from inference to direct observation. The descent to these locations had required machines that could endure conditions far outside ordinary experience. Nearly 2.5 miles beneath the surface, light from above no longer reached, and pressure pressed inward with a constant, immense force. It was within this depth that cameras, fixed to remotely operated vehicles, recorded structures unlike anything previously seen in this region of the ocean. What appeared on those recordings did not resemble the soft, layered plains many had once imagined. Instead, the seafloor rose into formations that seemed almost constructed, narrow towers extending upward from the ground, their surfaces textured and irregular. Around them, plumes of dark fluid moved steadily into the surrounding water, not dispersing immediately, but holding their shape for a moment before blending into the cold environment. These were hydrothermal vents, sites where heated fluids emerge from beneath the crust, carrying dissolved minerals gathered during their passage through the earth. When these fluids meet the surrounding seawater, the sudden change in temperature causes the minerals to solidify, gradually building the structures seen in the footage. Over time, this process creates vertical formations that can grow taller and more complex, shaped by the flow that sustains them. The images revealed more than the presence of these features. They showed activity, movement, and a sense of ongoing formation. The plumes rose continuously, suggesting a system that operates without pause, driven by processes occurring far below the visible surface of the seabed. The surrounding area appeared altered by this activity, with surfaces coated in deposits that reflected the chemistry of the escaping fluids. For many who encountered these images, the effect was subtle yet profound. The Indian Ocean, long understood through charts and measurements, was now presenting itself in a more direct way. The vents did not appear as abstract data points, but as physical structures occupying space, interacting with their surroundings in real time. The timing of these observations also mattered. By the early 2000s, similar features had been studied in other oceans, yet the Indian Ocean remained less documented. The arrival of these images filled a gap, extending known patterns into a region that had previously been defined by its absence of visual records. It confirmed that the processes shaping the deep ocean were not isolated, but part of a broader system that extended across multiple basins. At the same time, the specific appearance of these vents carried its own character. Their arrangement, their scale, and the environment around them reflected the local conditions of the seafloor, shaped by the geological setting described only indirectly before. What had once been understood through models and scattered measurements now gained a form that could be observed, studied, and compared. These first images did not complete the picture of the Indian Ocean's depths, Instead, they marked a transition, a moment when the unseen began to enter the realm of the visible. The seafloor, once mapped through sound and sampling, now revealed parts of itself through direct sight, allowing its structures to be understood not only through data, but through presence. In the recorded scenes from those depths, some structures stand apart, not only for their shape, but for the process that sustains them. They rise with a vertical clarity that contrasts with the surrounding ground, as if assembled piece by piece, guided by a steady and unseen force. Their surfaces appear dark and textured, their outlines sharp against the faint glow of instrument lights. These formations are known as black smokers, though the name carries a simplicity that does not fully reflect their complexity. At their core is a continuous exchange between water and the heated interior of the earth. Seawater moves downward through fractures in the crust, traveling into regions where temperatures increase far beyond those of the surrounding ocean. In these depths, the water does not behave as it would at the surface. It becomes enriched with dissolved metals and minerals, drawn from the rocks it passes through. As this altered water finds its way back upward, it carries both heat and material toward the seafloor. When it emerges, it encounters the cold ocean environment, and the sudden contrast triggers a rapid transformation. Minerals that had remained dissolved begin to solidify almost instantly, forming tiny particles that give the fluid its dark appearance. These particles drift outward, creating the visual effect that gave these vents their name. At the same time, not all of the material disperses. Some of it settles directly around the opening, accumulating layer by layer. With each pulse of mineral-rich fluid, new deposits are added, gradually building the structure upward. Over extended periods, this process creates chimney-like forms that can reach considerable heights, their growth shaped by the flow that feeds them. The result is a landscape that carries a distinct sense of form and structure. The towers do not appear random, but organized, as if guided by a consistent pattern. Their vertical alignment and defined edges suggest a kind of construction, though no hands shape them. Instead, chemistry and temperature act as the quiet architects, working through repetition rather than intention. Light from exploration equipment reveals surfaces that are both rough and intricate, marked by the continuous layering of mineral deposits. Openings near the top release ongoing streams of heated fluid, maintaining the cycle that allows the structure to persist. If the flow slows or shifts, growth changes as well, sometimes stopping, sometimes redirecting to form new openings nearby. What emerges from this process is not static. These towers exist in a state of gradual change, shaped by conditions that remain active beneath them. They may grow, erode, or collapse over time, depending on the balance between mineral deposition and the surrounding environment. Each structure reflects the specific conditions of its location, including temperature, chemical composition, and the movement of fluids through the crust. There is a quiet precision in how these forms develop. Without light, without surface influence, and without direct observation, the seafloor gives rise to structures that carry a sense of deliberate shape. Their presence suggests that even in complete darkness, the interaction between water and rock can produce patterns that resemble construction. Within this setting, the deep ocean reveals another layer of its character, where natural processes give rise to forms that feel both unfamiliar and strangely ordered, shaped entirely by forces that operate beyond sight. Long before any image revealed structures on the seafloor, a deeper assumption guided how life itself was understood. Nearly every known ecosystem at the surface traced its energy back to sunlight, carried through green leaves, drifting algae, and the quiet work of photosynthesis. It was a pattern so consistent that it felt complete, as if all living systems shared the same distant source. Then, in the depths of the Indian Ocean, that pattern began to loosen. Around active vent fields, where heated fluids enter the surrounding water, researchers encountered communities that did not rely on light at all. There, in a place where sunlight has no presence, life organizes itself through a different pathway. At the base of these systems are microorganisms, too small to see without magnification, yet central to everything that surrounds them. These microbes do not draw energy from the sun. Instead, they depend on chemical compounds released from within the earth. As mineral-rich fluids move through the seafloor and emerge into the ocean, they carry substances such as hydrogen sulfide and other reduced chemicals. The microbes use these compounds as an energy source, converting them into organic material through a process known as chemosynthesis. In this process, chemistry replaces light as the driving force. The microbes build the foundation of an ecosystem not by capturing sunlight, but by transforming chemical gradients into usable energy. Their activity produces organic matter that supports a wider network of life, forming the base of a food web that develops entirely in darkness. Around these microbial communities, larger organisms find a way to exist within this alternative system. Some host the microbes within their own bodies, forming close associations that allow them to access the energy produced through chemical reactions. Others feed directly or indirectly on the products of these processes, creating layers of interaction that mirror surface ecosystems yet arise from a completely different origin. The existence of such systems extends beyond a single location. It suggests that life does not require the presence of sunlight in the way once assumed. Instead, it reveals that as long as there is a source of energy, even one rooted in the Earth's internal chemistry, biological systems can emerge and persist. This understanding reshapes how scientists think about the boundaries of life. It broadens the concept of habitable environments, not only within the ocean, but across the planet and beyond. Conditions once considered too extreme or too isolated now appear less restrictive as the essential requirement shifts from light to energy in its many possible forms. There is a quiet shift in perspective that accompanies this realization. The deep ocean no longer appears as a place defined by absence, but as one shaped by processes that operate under different rules. The presence of these ecosystems suggests that life can adapt to conditions far removed from those experienced at the surface, finding pathways that were once unimagined. Within the Indian Ocean, these communities exist as part of a larger, interconnected system tied to geological activity and the movement of chemical compounds through the crust. Their presence does not stand apart from the surrounding environment, but arises directly from it, reflecting the intimate connection between the living and the non-living world. In this way, the discovery of life without sunlight becomes less a single moment of surprise and more a gradual unfolding, revealing that the conditions supporting life are more varied and more deeply rooted in the planet's structure than once believed. At the edges of those mineral-rich outflows, movement begins to take shape, not as drifting silhouettes from above, but as a gathering of forms that belong entirely to this environment. What appears in these regions does not resemble the familiar patterns of coastal life. Instead, bodies seem arranged according to a different set of constraints, shaped by conditions that have no direct parallel at the surface. Clusters of organisms settle close to the sources of chemical energy, where the surrounding water carries both warmth and dissolved compounds. Among them are snails with shells that vary in texture and thickness, some smooth, others layered with deposits drawn from the environment itself. Nearby, shrimp move in loose groups, their bodies often pale or translucent, adapted to a world without light. Mussels attach themselves in dense groupings, anchored firmly to the substrate, their soft tissues housing internal systems that connect them to the chemistry around them. Barnacles appear as small enclosures fixed to solid surfaces, opening and closing in rhythms that follow the movement of water. Each of these animals exists within a narrow range of conditions, positioned carefully along gradients of temperature and chemical concentration. Too far from the source, and the energy that sustains them fades. Too close, and the intensity becomes difficult to withstand. Their forms reflect this balance. Many lack pigmentation, their coloration subdued or absent, as light plays no role in their survival. Some possess elongated appendages or specialized surfaces that increase contact with the surrounding water, allowing them to absorb or interact with the compounds they depend on. Others maintain internal relationships with microorganisms, forming associations that allow them to draw nourishment indirectly from chemical processes occurring within their own bodies. The pace of life in these regions differs as well. Growth, movement, and reproduction are all shaped by the availability of energy and the stability of the environment. Some species develop slowly, their lifespans extending across years in conditions that remain relatively constant. Others respond more quickly to changes, adjusting their position or behavior as the flow of heated fluids shifts over time. Pressure plays a constant role, compressing every structure and influencing how tissues are formed and maintained. The absence of sunlight removes the need for visual signaling, and so many features that define surface animals are reduced or entirely absent. Instead, sensory systems may rely on chemical detection or subtle changes in water movement, guiding organisms through an environment where visibility holds little meaning. Interactions between species form a network that is both intricate and localized. Predation, competition, and cooperation all occur within this confined setting, shaped by the limited space and the dependence on a single energy source. The result is a community that feels cohesive, each part connected to the same underlying process. As more observations accumulate, the sense of unfamiliarity begins to deepen. These animals are not simply unusual variations of known forms, but expressions of a different set of possibilities. Their existence suggests that when conditions change fundamentally, biology follows, adapting in ways that extend beyond the patterns seen elsewhere. Within the Indian Ocean, these communities contribute to a broader understanding of life's adaptability. The organisms that inhabit these depths do not rely on the cycles that govern surface ecosystems. Instead, they persist within a framework defined by heat, chemistry, and pressure, forming systems that are stable in their own way, yet entirely distinct. In their presence, the deep ocean reveals a dimension of life that feels distant from everyday experience, not through exaggeration, but through the quiet reality of forms shaped by an environment that operates on different terms. Among the organisms that gather near these active zones, one stands apart in both form and composition, as though shaped by conditions that pressed beyond the usual limits of biology. Its shell coils in a familiar spiral, yet what lies beneath that curve departs from expectations in a quiet but striking way. This is the scaly foot snail, a species known only from a small number of vent fields within the Indian Ocean. Its range is narrow, confined to environments where the balance of heat and chemistry remains stable enough to sustain it. Within this limited space, it has developed features that reflect a close and prolonged interaction with the materials present in its surroundings. Covering the lower part of its body are structures that resemble overlapping scales, arranged in a way that creates a flexible but protective layer. These scales are not composed solely of organic material. They incorporate iron compounds drawn from the surrounding environment, giving them a density and resilience that is unusual among known animals. The integration of metal into living tissue forms a surface that can withstand conditions that would otherwise be damaging. The shell itself carries a similar influence. It is layered in a way that combines organic and mineral components, creating a composite structure that provides both strength and durability. The presence of iron sulfide within these layers contributes to its dark appearance, aligning its form with the chemistry of the vent systems it inhabits. Beneath these external features, the snail maintains a relationship that defines how it survives. Within its body are specialized tissues that house bacteria, organisms capable of using chemical compounds as a source of energy. These bacteria carry out processes that convert those compounds into organic material, effectively producing nourishment from the environment's chemistry. Rather than feeding in the way most animals do, the scaly foot snail depends on this internal system. The bacteria function as a source of sustenance, their activities supporting the host in a continuous exchange. The snail provides a stable environment, while the bacteria supply the energy needed for growth and maintenance. This arrangement removes the need for traditional feeding behavior, linking the animal directly to the chemical processes occurring around it. Its movement remains slow and deliberate, limited by the conditions of its habitat. It does not travel far from the areas where these chemical resources are available. The boundaries of its world are defined not by physical barriers, but by the presence of the specific conditions that sustain both the snail and its internal partners. The existence of such an organism suggests a path of adaptation that follows the environment closely, integrating external materials into biological structure and relying on internal relationships for survival. Each aspect of its form reflects the pressures and opportunities presented by its surroundings, from the composition of its protective layers to the nature of its nutrition. What emerges is a creature that appears almost constructed from the elements of its habitat, shaped by chemistry as much as by biology. Its features may seem unfamiliar, yet they arise from processes that remain consistent, guided by the interaction between living systems and the materials available to them. Within the Indian Ocean, the scaly foot snail exists as a precise expression of these conditions, its form and function aligned with a setting that allows such characteristics to develop. There is a part of the Indian Ocean where change unfolds at a pace so gradual that it almost escapes notice, measured not in moments, but in the quiet accumulation of years. Along the southwest Indian Ridge, the separation of tectonic plates proceeds with an unusual restraint, making it one of the longest stretches on Earth where new seafloor forms at a very slow to ultra-slow rate. Here, the movement of the crust is reduced to a subtle divergence, often only a few millimeters each year. This slow opening alters the character of the ridge itself. Instead of broad, elevated features, the landscape becomes more fragmented, with deeper valleys and exposed sections of the Earth's interior appearing closer to the surface of the seabed. The usual layering of volcanic material can be thinner or interrupted, revealing rocks that form deeper within the planet before being brought upward. This pace of formation influences how heat moves through the crust. With less frequent volcanic activity, the distribution of heat becomes uneven, concentrated in specific areas rather than spread evenly along the ridge. In these localized zones, the interaction between seawater and underlying rock takes on a different intensity, shaping the chemical conditions that emerge from below. The systems that develop in this environment reflect those differences. Fluids circulating through the crust may encounter varied compositions of rock, leading to changes in the minerals they carry and the temperatures they reach. When these fluids return to the seafloor, they do so with characteristics that differ from those found in faster spreading regions. The result is a set of conditions that are less uniform, more varied, and in some cases, more revealing of the processes at work beneath the surface. For scientists, this slow spreading ridge offers a rare opportunity to observe aspects of seafloor formation that are often hidden elsewhere. Because the creation of new crust occurs at a reduced pace, features that would normally be buried or reshaped by ongoing activity can remain visible for longer periods. This allows for closer study of how different layers form, how fractures develop, and how chemical exchanges take place over time. The structure of the ridge itself carries these signatures. Deep axial valleys trace the line where the plates are pulling apart, bordered by rugged terrain that reflects both tectonic movement and limited volcanic resurfacing. The absence of rapid accumulation allows the underlying framework to remain more exposed, offering a clearer view into the architecture of the ocean floor. In this setting, the relationship between movement and form becomes more apparent. The rate at which the plates separate does not simply control how quickly new material is added. It shapes the entire environment, influencing temperature, chemical composition, and the arrangement of geological features. Each of these factors, in turn, affects the systems that develop in and around the ridge. What emerges is a landscape defined not only by its structure, but by the tempo of its formation. The southwest Indian Ridge reveals that even small differences in speed can lead to distinct outcomes, creating conditions that differ from those found in regions where the Earth opens more rapidly. Within the broader context of the Indian Ocean, this ridge adds another layer of complexity, showing that the nature of the seafloor is shaped as much by how quickly it changes as by the forces that drive it. At certain points beneath the Indian Ocean, lines of separation do not run alone. They converge, meeting in quiet intersections where the motion of the Earth becomes more intricate. These are places where multiple ridge systems connect, forming junctions that carry the combined influence of several tectonic boundaries at once. One of these intersections lies near the Rodriguez Triple Junction, a region where three spreading centers approach and meet beneath the sea. Each of these ridges marks a zone where plates move apart, yet at this point, their paths intersect, creating a configuration that is both balanced and dynamic. The crust here is not guided by a single direction of motion, but by the interaction of several, each pulling gently yet persistently. The geometry of such a junction shapes the surrounding seafloor in subtle ways. Instead of a single linear ridge, the terrain forms a network of connected segments, each adjusting to the movement of its neighbors. The result is a landscape that reflects constant adjustment, where boundaries shift slightly over time, maintaining a balance between the forces acting upon them. Beneath this arrangement, the crust experiences a continuous process of stretching and renewal. As plates diverge along each branch of the junction, new material rises to fill the gaps, solidifying and becoming part of the ocean floor. The interaction between these branches influences how this material is distributed, sometimes concentrating activity in certain areas while leaving others comparatively quiet. Fractures and faults develop in response to these movements, tracing lines that extend outward from the junction. Through these pathways, heat and chemical exchanges occur, linking the deeper layers of the Earth to the seafloor environment. The pattern is not uniform, but shaped by the combined influence of the three meeting ridges, each contributing to the overall structure. In regions like this, the idea of a stable boundary becomes less distinct. The crust is in a state of ongoing rearrangement, adjusting to the shifting balance between plates. This movement does not produce sudden change, but a steady reconfiguration that unfolds over long periods. The seafloor reflects this process through its varied topography, with features that align along different directions, marking the influence of each ridge. What emerges from such a setting is not immediately visible in terms of living systems, but it establishes the conditions from which those systems can arise. The distribution of heat, the pathways for fluid movement, and the composition of the crust are all shaped here, forming a foundation that extends outward from the junction. In this way, the Rodriguez triple junction represents a point where geological processes become especially intertwined. It is a place where the Earth's outer layer is not only opening, but doing so in coordination with multiple forces, creating a pattern that is both complex and continuous. Understanding these intersections shifts attention toward the underlying structure of the ocean floor. It suggests that many of the features observed in deeper studies are rooted in the way the crust is organized and in motion. The presence of such junctions highlights that beneath the Indian Ocean, the most fundamental changes begin not with what lives there, but with the quiet, persistent movement of the planet itself. On a shoreline shaped by waves and volcanic rock, the sand holds grains that carry a time far older than the land beneath them. Each grain appears ordinary at a glance, pale and worn by the movement of water, yet within some of them lies a record that does not belong to the island where they rest. Mauritius is a young place in geological terms, formed through volcanic activity rising from the ocean floor. Its rocks speak of recent origins, built from molten material that cooled and solidified long after older continents had already taken shape elsewhere. By all expectations, the minerals found along its beaches should reflect that youth, composed of materials consistent with its volcanic history. Yet, among these grains, researchers identified zircon crystals whose ages extend far beyond the island itself. These crystals can endure immense spans of time, preserving within their structure a record of when they first formed. When analyzed, some revealed ages reaching into hundreds of millions, even billions of years, far older than the volcanic layers that make up Mauritius. This contrast between the island's youth and the crystal's age presented a quiet inconsistency. The zircons could not have originated from the volcanic processes that created the island. Their presence suggested that older material existed nearby, material that had been incorporated into the younger rocks or carried to the surface through geological processes not immediately visible. From this observation emerged the idea of Marishia, a proposed microcontinent whose fragments now lie hidden beneath parts of the Indian Ocean. Rather than a single intact landmass, it is understood as remnants of ancient continental crust, pieces that were once part of a larger configuration of land before being separated and submerged. The formation of such fragments traces back to the long history of continental movement. As larger landmasses shifted and broke apart, sections of crust could become isolated, thinned, and eventually covered by volcanic activity, or submerged beneath the ocean. Over time, these fragments might remain buried beneath newer layers, their presence detectable only through indirect evidence. In the case of Mauritius, volcanic processes likely brought small portions of this older crust closer to the surface. As molten material rose, it may have carried zircon crystals upward, embedding them within younger rocks that would later erode and release them onto the island's beaches. In this way, the grains found at the shoreline become traces of a deeper and older structure, one that remains largely hidden. The concept of Marishia does not describe a lost land in the sense of disappearance, but a transformation. The material that once formed part of a continent has not vanished, but has been altered, fragmented, and concealed beneath layers that formed later. Its existence is inferred through the persistence of minerals that record its earlier state. There is a certain stillness in this form of discovery. It does not arise from direct observation of large structures, but from the careful study of minute details, each crystal holding information that points beyond itself. The scale of the evidence remains small, yet its implications extend across vast stretches of time and space. Within the Indian Ocean, Marishia represents a hidden layer of history, one that lies beneath more recent formations. It suggests that the seafloor is not only shaped by ongoing processes, but also carries remnants of earlier worlds, preserved in fragments that endure long after their original context has changed. In these grains of zircon, the past remains present, not as a visible landscape, but as a quiet record embedded within the materials of the earth itself. A single grain of sand can pass unnoticed between fingers, carried by wind or tide, without drawing attention to itself. Its surface appears simple, shaped by motion and time, offering no immediate hint of the history it contains. Yet, within certain grains, there are structures that have endured since a far earlier chapter of the planet, holding a record that remains intact despite the passage of immense spans of time. Zircon is one such mineral, small in size yet remarkable in its ability to preserve age. Its internal structure resists alteration, allowing it to retain information about the moment it formed. When conditions are right, it incorporates elements that slowly change in predictable ways, providing a method for tracing its origin far back into geological history. Through careful measurement, these crystals become markers of time, each one carrying a precise indication of its formation. In Mauritius, the presence of zircons that predate the island itself creates a quiet but significant contrast. The volcanic rocks that define the island are relatively recent, yet the crystals found within them point to origins that extend hundreds of millions, even billions of years into the past. This difference is not subtle, and it cannot be explained by the processes that formed the island alone. The implication is that these zircons were not created in place, but inherited from older material. Their existence suggests that fragments of ancient continental crust lie beneath or near the volcanic layers, hidden from direct view. The crystals act as remnants of that older foundation, carried upward and embedded within younger rock before eventually appearing at the surface through erosion. Each zircon, though minute, becomes a fragment of a much larger story. It indicates that beneath the visible structure of the island, there are pieces of a landmass that once existed in a different form. These fragments have been altered, buried, and reshaped, yet they persist in subtle ways, leaving behind traces that can be detected through careful study. There is a certain stillness in how this evidence presents itself. The crystals do not reveal their history through size or prominence, but through the information they hold. Their scale remains small, yet their significance extends across vast distances and timescales, connecting the present landscape to formations that no longer exist in their original form. The ability of zircon to endure also reflects the stability of certain materials within the Earth's crust. While surrounding rocks may melt, fracture, or erode, these crystals can survive, passing through multiple cycles of geological change without losing their identity. In this way, they serve as carriers of continuity, linking different phases of the planet's evolution. From these grains, scientists reconstruct a picture that would otherwise remain hidden. The presence of ancient zircons within a young volcanic setting points toward a layered structure where older continental fragments remain beneath newer formations. It suggests that the history of the region is not limited to what is visible, but includes deeper and more complex foundations. In the Indian Ocean, this realization adds another dimension to the understanding of its seafloor. Beneath areas that appear recent in origin, there may lie remnants of far older landscapes, preserved in fragments that only reveal themselves through careful observation. The crystals found in Mauritius become one such indication, a quiet signal of something larger that has been altered but not erased. Within these small and enduring forms, the scale of geological time becomes tangible, held within structures that can rest unnoticed until their significance is brought into view. On long timescales, land does not disappear in sudden moments, nor does it sink as a single piece into the ocean below. Instead, it changes shape slowly, drawn outward, thinned, and divided as the surface of the earth shifts in ways that are almost imperceptible within a single lifetime. What seems permanent at one moment can, over immense spans, become rearranged into fragments that no longer resemble their origin. The story of Marishia is linked to such a transformation, connected to an earlier configuration of land that once joined regions, now separated by ocean. Long ago, the areas that would become India and Madagascar were part of a larger continental arrangement. Over time, forces within the earth began to pull these regions apart, initiating a process that unfolded gradually across millions of years. As separation progressed, the crust between these emerging landmasses did not remain intact. It stretched, becoming thinner, and in some places fractured into smaller segments. These segments did not always move in the same way as the larger plates. Some were carried along, while others remained behind, caught between diverging regions and gradually isolated. During this process, volcanic activity played a significant role. As the crust opened, molten material rose from below, forming new layers of rock that spread across parts of the seafloor. In areas where older continental fragments remained, these newer volcanic layers could cover them, concealing their presence beneath a more recent surface. Over time, this covering became thicker, further separating the older material from direct observation. The result is not a clear boundary between what was once land and what is now ocean. Instead, there exists a layered structure, where fragments of continental crust lie beneath younger formations, preserved but hidden. These fragments retain the characteristics of their origin, even as the environment around them has changed. Marishia is understood as one such fragment, not a complete continent in its original form, but a collection of pieces that once belonged to a larger whole. Its existence reflects the way continents can be reshaped without fully disappearing, their material redistributed and concealed rather than lost entirely. This process differs from the idea of land vanishing in a singular event. It is not a disappearance, but a transformation that occurs through stretching, breaking, and burial. Each stage leaves traces, though they may be subtle, requiring careful interpretation to identify. Minerals preserved within younger rocks, variations in crustal thickness, and patterns in the structure of the seafloor all contribute to the reconstruction of what once existed. Over extended periods, these fragments may remain stable beneath the ocean, their presence influencing the regions above them in ways that are not immediately visible. They form part of the deeper architecture of the Earth, underlying newer features while retaining a connection to earlier configurations. In the Indian Ocean, this layered history adds another dimension to the understanding of its seafloor. Beneath areas shaped by more recent processes, there are remnants of older landscapes carried forward through cycles of change. The surface may reflect the present, but the structure below carries a memory of what came before. Through this perspective, the idea of a lost continent becomes less about absence and more about continuity. The material that once formed part of a larger landmass still exists, altered in form and position, yet preserved within the evolving structure of the planet. In many parts of the Indian Ocean, the seafloor rises abruptly from its surroundings, forming steep elevations that interrupt the otherwise gradual contours below. These structures, known as seamounts, extend upward from great depths, sometimes reaching close to the surface, yet remaining entirely submerged. Their slopes are often rugged, their peaks irregular, and their presence alters the movement of water in ways that are not immediately visible from above. Unlike the broader features of the seabed, seamounts create localized environments defined by their shape and position. As ocean currents encounter these underwater mountains, they are forced to change direction, flowing upward along the slopes and accelerating around the sides. This movement brings deeper water toward higher levels and redistributes suspended particles that drift through the ocean. Through this interaction, materials that might otherwise settle evenly across the seafloor become concentrated around these elevated regions. Nutrients carried within the water are lifted and mixed, creating conditions that differ from those found in the surrounding depths. The result is a setting where certain forms of life find a more stable or abundant supply of resources. The surfaces of seamounts also provide something that is less common in deeper areas: exposed rock. While large stretches of the seabed are covered in soft sediment, the slopes of these underwater mountains often remain uncovered, shaped by currents that prevent the accumulation of fine particles. This exposed substrate becomes a place where organisms can attach and grow. Corals, sponges, and other stationary animals establish themselves along these surfaces, forming communities that depend on both the structure of the seamount and the flow of water around it. Their forms vary, some branching outward, others spreading across the rock, each adapted to capture nutrients passing through the current. Over time, these organisms create layers of living material, adding complexity to the surface of the mountain. Around these attached communities, other species gather. Fish, crustaceans, and various mobile organisms move through the area, drawn by the availability of food and the presence of shelter provided by the growing structures. The seamount becomes a point of convergence, not because it produces life directly, but because it shapes the conditions that allow life to concentrate. Each seamount carries its own variation of this pattern. Differences in height, slope, and location influence how currents interact with the structure, leading to variations in the types of communities that develop. Some may support dense assemblages of organisms, while others host more dispersed populations, depending on the balance of factors present. For scientists, these underwater mountains reveal a form of organization within the deep ocean that is not immediately apparent when viewing it as a continuous expanse. They demonstrate that even in regions far from sunlight and coastal influence, physical features can guide the distribution of life, creating areas where biological activity becomes more concentrated. The significance of seamounts lies not in a single unusual species, but in the pattern they represent. Isolated structures rising from the seafloor become gathering points, shaping ecosystems through their interaction with water and material movement. They show that the deep ocean is not uniform, but structured in ways that influence where life can establish itself. Within the Indian Ocean, these formations contribute to a broader understanding of how life persists and organizes in the absence of familiar conditions. They stand as quiet examples of how shape and flow can bring together communities that would otherwise remain scattered across the depths. Movement in the deep ocean is rarely still, even where light never reaches. Water travels in slow, persistent paths, carrying with it fine particles, dissolved nutrients, and traces of organic material descending from far above. These motions are often subtle, yet when they encounter elevation rising from the seafloor, their patterns begin to change. As currents meet underwater high ground, they are forced to adjust, bending upward along slopes and accelerating as they pass around ridges and peaks. This shift alters how material moves through the water. Particles that might have settled elsewhere are lifted, suspended, and carried across surfaces that would otherwise remain quiet. In these regions, the flow becomes more active, redistributing resources in ways that do not occur across flatter terrain. The result is a concentration of usable material in specific areas. Organic fragments drifting through the water are more likely to remain in motion near these elevations, increasing the chances that organisms can encounter and use them. The water itself may carry higher levels of nutrients, shaped by the way currents interact with the underlying structure. At the same time, the nature of the seafloor changes. Elevated regions often expose solid rock, shaped by the continuous movement of water that prevents fine sediments from settling. This contrasts with the broader plains, where layers of soft material accumulate over time, creating surfaces that shift easily and offer little stability. For many organisms, the presence of hard substrate provides a foundation that is otherwise rare in deeper environments. Surfaces that remain firm allow animals to anchor themselves securely, maintaining position within moving water. This attachment enables them to extend structures into the flow, capturing passing particles or interacting directly with the surrounding environment. The combination of altered currents and stable surfaces creates conditions that support a higher density of life. Animals gather where these factors align, forming communities that are shaped by both the physical structure of the seafloor and the movement of water above it. Each species occupies a position that reflects its needs, whether that involves access to food, stability, or specific chemical conditions. These patterns are not random. They follow the contours of the landscape, tracing the lines where elevation changes and where currents respond. Even in the absence of light, the form of the seafloor guides the arrangement of living systems, influencing where organisms can settle and how they interact with one another. Over time, these clusters can become established, persisting as long as the conditions that support them remain stable. Changes in current strength, direction, or the structure of the seafloor can alter these communities, shifting the balance and redistributing life across the region. What emerges is an understanding that the deep ocean is structured in ways that extend beyond what is immediately visible. The distribution of life is not uniform, but shaped by an underlying architecture that directs movement and creates variation. Elevated features serve as focal points, not because they generate resources directly, but because they influence how those resources are delivered. In the Indian Ocean, this relationship between form and flow reveals a quiet order within the depths. The arrangement of the seafloor, though hidden, plays a central role in determining where life gathers, showing that even in darkness, structure continues to guide the patterns of existence. Far from the raised contours that interrupt the seafloor, there are regions where the ground settles into an almost continuous level, extending outward in all directions with little visible change. These are the abyssal plains, vast areas that occupy significant portions of the Indian Ocean, lying at depths where movement is subtle and variation becomes difficult to perceive. At first encounter, these plains can appear nearly featureless. Their surfaces stretch without sharp elevation or sudden interruption, forming a quiet expanse that contrasts with the more complex terrain found elsewhere. The absence of steep slopes or prominent structures gives an impression of stillness, as if the seafloor has reached a state of rest after long periods of change. Yet this apparent simplicity conceals a different kind of complexity. Over time, fine particles descend through the water column, settling gradually onto the seabed. These particles originate from many sources: fragments of organic material, microscopic remains, and mineral grains that drift downward at a slow and steady pace. Layer by layer, they accumulate, forming sediments that can reach considerable thickness. Within these sediments, a record is preserved. Each layer reflects the conditions present at the time of its deposition, carrying traces of biological activity, chemical composition, and environmental change. The plains become a kind of archive where the passage of time is recorded not in visible landmarks, but in the gradual buildup of material that holds subtle variations from one layer to the next. Life exists here as well, though it does not gather in dense or easily visible communities. Organisms are adapted to a setting where resources are limited and widely dispersed. Many live within the sediment itself, moving slowly through the fine material, while others rest on the surface, interacting with what arrives from above. Their forms tend to be understated, reflecting the need for efficiency in an environment where energy is scarce. The scale of these plains contributes to their significance. They extend across distances that can be difficult to grasp, covering areas larger than many surface landscapes. This vastness creates a sense of continuity, where the same conditions persist over long stretches, shaping the types of organisms that can survive and the processes that occur within the sediment. Movement across these regions is gradual. Currents pass overhead, but their influence at the seafloor is often reduced, allowing particles to settle undisturbed. The environment remains relatively stable, with changes occurring over long periods rather than through sudden events. This stability allows for the preservation of delicate structures within the sediment, maintaining a record that can be studied to understand past conditions. The absence of dramatic features does not diminish the importance of these plains. Instead, it highlights a different aspect of the ocean's character, where scale and subtlety define the landscape. The processes at work are continuous and persistent, shaping the seafloor in ways that are not immediately visible, yet deeply significant. Within the Indian Ocean, the abyssal plains form a broad foundation, supporting both the accumulation of material and the presence of life adapted to quiet conditions. They represent a form of complexity that emerges not from variation in shape, but from the accumulation of time and the persistence of gradual processes. In this still and expansive setting, the deep ocean reveals a quieter dimension, one defined by breadth, continuity, and the slow layering of history across an almost endless surface. Across certain stretches of the abyssal plains, the surface does not remain entirely smooth. Resting upon the fine sediments are scattered objects, rounded and dark, each one distinct from the surrounding material. They lie exposed, spaced irregularly across the seafloor, neither buried nor fully elevated, forming a pattern that becomes more apparent the longer one observes. These are polymetallic nodules, mineral formations that develop slowly through the gradual accumulation of elements dissolved in seawater. Over extended periods, metals such as manganese, cobalt, copper, and nickel gather around a central nucleus, which may be a small fragment of shell, a grain of sediment, or another particle resting on the seabed. Layer upon layer, the nodule grows outward, each addition forming a thin coating that builds over time. The pace of this growth is remarkably slow. A nodule may increase in size by only a few millimeters over the span of 1 million years, reflecting a process that unfolds with almost imperceptible change. Unlike the more dynamic formations found in other parts of the ocean, these structures develop through steady deposition, guided by chemical conditions that remain stable over long durations. Their surfaces often appear textured, sometimes smooth, sometimes marked by small irregularities that reflect variations in the environment during their formation. Each layer carries information about the conditions present at the time it was added, making the nodules a form of natural record. By studying their composition and structure, scientists can gain insight into changes in ocean chemistry and the history of material movement across the seafloor. Despite their mineral nature, these nodules do not exist in isolation from living systems. Their presence introduces a form of structure into an environment otherwise dominated by soft sediment. For certain organisms, this solid surface provides an opportunity to attach, rest, or seek shelter. Small creatures may inhabit the spaces between nodules, while others settle directly upon them, forming subtle associations that link life to these slowly growing formations. In areas where nodules are abundant, the seafloor becomes a mosaic of hard and soft elements, each influencing how organisms distribute themselves. The nodules create microenvironments, offering surfaces that differ from the surrounding sediment in texture and stability. This variation supports a range of life forms that might not otherwise find suitable conditions in a more uniform setting. The significance of these formations extends beyond their biological role. Their composition, rich in multiple metals, has drawn attention for potential resource extraction. The idea that the seafloor holds concentrations of valuable elements introduces a different dimension to their presence, one that connects scientific interest with considerations of use and impact. At the same time, their slow formation highlights the scale at which they exist within the Earth's systems. Removing or disturbing them would affect structures that have taken immense periods to develop, altering environments that change only gradually under natural conditions. This contrast between their value as resources and their role as part of a long evolving system adds a layer of complexity to how they are understood. Within the Indian Ocean, polymetallic nodules represent a quiet intersection of geology and biology. They are both objects shaped by chemical processes and surfaces that support living communities. Their presence transforms the seafloor into a place where even the smallest formations carry significance, linking the movement of elements with the persistence of life across vast and still landscapes. Beneath the shifting surface of the Indian Ocean, there are places where time settles instead of moving on. In these regions, the seafloor gathers traces of events that unfolded long before any direct observation, storing them in forms that remain quiet yet persistent. What appears as sediment or mineral crust becomes, on closer study, a layered record of processes that have continued over immense spans. Each deposit carries within it a sequence, a gradual accumulation of material shaped by chemical conditions that change slowly across centuries and beyond. Fine particles descending from above combine with substances formed in place, creating structures that hold subtle differences from one layer to the next. These differences, though often invisible at a glance, contain information about the environment at the time of their formation. In certain areas, methane seeps introduce another dimension to this record. Here, gas originating from deeper within the earth moves upward through the seafloor, interacting with surrounding water and sediment. As methane emerges, it encounters microorganisms capable of transforming it through chemical reactions. These processes alter the composition of the surrounding environment, leading to the formation of carbonate deposits that accumulate gradually over time. These carbonate structures form in response to the presence of methane, capturing the conditions under which the seepage occurred. As layers build upon one another, they create a sequence that reflects periods of activity, variation, and relative stillness. By examining these layers, scientists can reconstruct patterns of methane release, identifying changes that may have taken place over extended intervals. The significance of these records lies in their continuity. Unlike visible features that may change or disappear, these chemical traces remain embedded within the seafloor, preserving a history that can be read through careful analysis. Each deposit becomes a point of reference, linking present observations to past conditions in a way that extends beyond direct measurement. This perspective shifts the understanding of the deep ocean. The seabed is not only a physical space defined by its shape and structure, but also a repository of information where chemical processes leave lasting marks. These marks are not always immediately apparent, yet they form a network of evidence that can be studied to reveal the evolution of the environment over time. In the Indian Ocean, this hidden archive complements the more visible features that have been observed elsewhere. While ridges, basins, and biological communities provide insight into current conditions, the sediments and mineral deposits offer a view into what has occurred across longer periods. Together, they create a more complete understanding, combining present structure with past activity. The study of these chemical records requires a different approach, one that focuses on detail rather than scale. Samples must be collected and examined closely, their composition analyzed to identify the processes that shaped them. Through this work, patterns begin to emerge, connecting isolated observations into a broader narrative of change. Within this quiet accumulation, the deep ocean reveals itself as a place where history is continuously written and preserved. The layers beneath the Indian Ocean hold not only material, but information. Capturing the interplay between geology and chemistry in forms that endure long after the events themselves have passed. In this way, the seabed becomes more than a surface. It becomes a record, holding within it the traces of processes that continue to shape the ocean, even when they remain unseen. In certain quiet regions of the seafloor, there are places where the ground releases a slow, invisible stream. The water above shows no obvious disturbance, yet beneath it, methane moves upward from deeper layers, passing through sediment and into the ocean. This movement is steady rather than forceful, creating zones where chemistry shifts in subtle but persistent ways. These areas are known as methane seeps, and their presence introduces a different kind of energy source into the deep ocean. Unlike the concentrated outflows associated with other environments, the release here is often diffuse, spreading through the seabed in a manner that does not immediately draw attention. Over time, however, the chemical conditions around these seeps become distinct, shaping the environment in ways that allow certain forms of life to emerge. At the foundation of these systems are microorganisms capable of using methane as a source of energy. Through specialized processes, they convert this gas into organic material, forming the base of a food web that develops without reliance on light. These microbes often exist within the sediment itself, where methane concentrations are sufficient to sustain their activity. Their presence alters the surrounding chemistry, creating gradients that extend outward from the seep. As these processes continue, the environment begins to support a wider range of organisms. Some animals host these microbes within their tissues, forming internal associations that allow them to draw nourishment from chemical reactions. Others feed on the microbial communities or on material produced through their activity, creating layers of interaction that expand outward from the source of methane. The physical appearance of these habitats can vary. In some locations, the interaction between methane and seawater leads to the formation of carbonate structures, building solid features that rise slightly above the surrounding sediment. These formations provide surfaces where organisms can attach, adding another layer of structure to the environment. In other areas, the seep remains less visible, defined primarily by changes in chemistry rather than by distinct physical features. The conditions within these systems differ from those found in other deep environments, even when both are based on chemical energy. The nature of methane as a fuel, the way it moves through sediment, and the reactions it undergoes all contribute to a distinct set of circumstances. These differences influence which organisms can survive, how they interact, and how the community develops over time. What becomes apparent is that life in the deep ocean does not depend on a single pathway. Instead, multiple systems exist, each based on different chemical processes that provide the energy needed to sustain biological activity. Methane seeps represent one such system, expanding the range of conditions under which life can persist. In the Indian Ocean, these environments add to the growing understanding of how diverse deep-sea ecosystems can be. They show that even within darkness, variations in chemistry can lead to different forms of organization, each adapted to the specific conditions present. The presence of methane seeps suggests that the deep ocean holds more than one method for supporting life beyond sunlight. It reveals a network of possibilities where energy can be drawn from sources that remain hidden beneath the seafloor, shaping communities that develop in response to those unseen flows. In this quiet exchange between gas and sediment, the ocean continues to reveal systems that extend beyond earlier expectations, each one grounded in the interaction between the Earth's interior and the water above. Far from where rivers meet the sea, their influence continues in ways that are not immediately visible. Long after fresh water disperses into the ocean, the material carried within it begins a separate journey, one that leads downward through the water column and outward across the seafloor. Over time, this movement creates structures that are not defined by sudden formation, but by steady accumulation. The Ganges sediment cone is one such structure, formed from the continuous delivery of particles originating far inland. The river gathers material as it flows, eroding rock, carrying soil, and transporting fine grains across vast distances before releasing them into the ocean. Once these particles enter deeper water, they begin to settle, guided by gravity and the slow movement of currents. This process does not produce immediate change. Instead, it unfolds gradually as each layer of sediment rests upon those that came before. Over immense spans of time, these layers build into a deposit of remarkable scale. The Ganges cone extends across a wide area of the seafloor, reaching thicknesses that reflect the persistence of this accumulation. It stands as one of the largest sedimentary structures on Earth, not shaped by eruption or upheaval, but by the quiet addition of countless individual grains. The formation of such a deposit depends on a balance between supply and distribution. Sediment arriving from the river does not fall straight downward in a uniform pattern. It is carried by underwater flows, spreading outward and settling in ways that reflect both the movement of water and the shape of the seabed. This distribution creates a broad, gently sloping structure, with variations that reveal changes in the conditions under which different layers were formed. Within these layers, information is preserved. Each deposit carries traces of the environment at the time it was laid down, including the composition of the material, the rate of accumulation, and the influence of currents. By studying these variations, scientists can reconstruct aspects of the past, identifying shifts in climate, changes in river flow, and other factors that influence the delivery of sediment. The scale of the Ganges sediment cone introduces a form of strangeness that differs from more immediate or visible discoveries. It is not defined by distinct shapes or dramatic features, but by its extent and continuity. Its presence reveals how small processes, repeated over long periods, can create structures that rival those formed through more rapid events. Life interacts with this environment in subtle ways. Organisms adapted to soft sediment inhabit the upper layers, moving through the fine material or resting upon it. Their presence contributes to the ongoing transformation of the deposit, mixing and altering the surface as new layers continue to arrive. The relationship between living systems and sediment becomes part of the larger process, linking biological activity with geological accumulation. In the Indian Ocean, the Ganges sediment cone represents a convergence of distant and local influences. Material originating from land becomes part of the deep seafloor, connecting environments that appear separate at first glance. The river's journey does not end at the coastline, but extends into the ocean, shaping regions far beyond its visible path. Through this gradual and continuous process, the seafloor records the passage of material across immense distances. The cone stands as a quiet reminder that some of the largest structures on Earth are built not through sudden change, but through persistence, where each grain contributes to a form that only becomes visible across time. Where the seafloor begins to descend from the edges of continents, the smooth transition is often interrupted by long, incised channels that cut downward into the margin. These features are submarine canyons, and they form a landscape that mirrors the valleys found on land, though hidden entirely beneath the ocean's surface. Their paths trace from shallower regions toward the deeper basins, creating routes through which material can move from one environment to another. Along the margins of the Indian Ocean, several of these canyons are shaped by the influence of major river systems. The Ganges, the Indus, and the Zambezi each contribute not only water, but also vast amounts of sediment carried from inland regions. When this material reaches the ocean, it does not simply disperse evenly across the seafloor. Instead, it can be guided into these submerged channels, where gravity and current work together to move it downslope. Within these canyons, sediment travels through processes that resemble slow, underwater flows. At times, denser mixtures of water and particles move along the canyon floor, carrying material into deeper areas of the ocean. These movements can occur intermittently, shaped by variations in supply and conditions, yet over long periods, they contribute to the transfer of large volumes of sediment. The structure of the canyons themselves reflects this activity. Their walls can be steep, their floors uneven, and their paths winding as they extend from the continental margin into the depths. Some branch into smaller channels, forming networks that distribute sediment across wider regions. The shape of each canyon depends on the interplay between the material moving through it and the underlying geology that guides its course. Though hidden from view, these valleys create a distinct topography beneath the ocean. They introduce vertical relief into areas that might otherwise appear gradual, forming routes that connect different depths. Along their sides and within their channels, variations in sediment type and stability provide conditions that differ from those found on adjacent slopes. Life responds to these differences in subtle ways. Organisms adapted to changing conditions may inhabit the canyon walls, while others occupy the floor, where transported material accumulates. The movement of sediment can influence the distribution of nutrients, creating localized environments that support specific communities. These patterns remain closely tied to the ongoing activity within the canyon, shifting as conditions evolve. The presence of submarine canyons also highlights a connection between distant environments. Material originating far inland is carried through rivers, delivered to the ocean, and then guided through these underwater pathways into deeper regions. In this way, processes occurring on land continue beneath the sea, linking surface landscapes with the hidden contours of the ocean floor. Over time, these canyons contribute to the shaping of the deep seafloor, distributing sediment that becomes part of larger depositional structures. Their role extends beyond simple transport, influencing how material is arranged and how different regions of the ocean develop. Within the Indian Ocean, this network of submerged valleys adds another layer to the understanding of its structure. It reveals that beneath the water lies a landscape marked by channels and slopes, shaped by forces that operate across both land and sea. In these unseen corridors, the movement of sediment continues quietly, tracing paths that connect distant origins to the depths, forming a hidden extension of the processes that shape the surface of the Earth. Along the southern edge of the Indonesian archipelago, the seafloor descends into a long, narrow depression where the surface of the Earth bends downward into itself. This is the Java or Sunda Trench, one of the deepest features within the Indian Ocean. It does not rise or spread outward like other formations, but instead marks a boundary where the crust is drawn beneath another, disappearing from view as it moves into the planet's interior. This region belongs to a class of geological settings known as subduction zones. Here, an oceanic plate approaches another plate and begins to sink beneath it, guided by differences in density and driven by the ongoing motion of the Earth's outer shell. The descent is gradual yet continuous, forming a trench that traces the line where one portion of the seafloor is being consumed. The shape of the trench reflects this process. Its slopes are steep, its floor narrow, and its depth extends far below the surrounding seabed. Sediment carried from nearby regions collects along its edges, while portions of the descending plate carry material downward, removing it from the surface environment. Over time, this movement reshapes the boundary, creating a dynamic landscape that evolves through persistent motion. This setting stands in contrast to regions where the crust is created. In areas where plates move apart, new material rises to form additional seafloor, expanding the ocean's surface. At the trench, the opposite occurs. Instead of formation, there is removal, as older crust is drawn downward and recycled within the earth. These two processes exist as parts of the same system, balancing one another across different regions of the ocean. The activity associated with subduction extends beyond the trench itself. As the descending plate moves deeper, it interacts with surrounding material, generating conditions that can lead to further geological changes. These interactions may influence volcanic activity in nearby regions, as well as the overall structure of the crust along the boundary. The Java Trench represents one of the most significant examples of this process within the Indian Ocean. While trenches are more common in other parts of the world, this system carries particular importance due to its scale and the role it plays in shaping the region. Its presence indicates that the ocean floor is not only expanding in some areas, but also being drawn inward in others, maintaining a balance that governs the long-term evolution of the planet's surface. The movement here is not visible in a direct sense, yet its effects are recorded in the structure of the seafloor and in the patterns of geological activity associated with it. Over extended periods, the descent of the plate continues, altering the composition and arrangement of material within the Earth. In this way, the trench becomes more than a physical feature. It represents a point within a larger cycle where the surface is continuously renewed through both creation and removal. The processes that shape it operate on scales that extend beyond immediate observation, yet they define the structure of the ocean floor in fundamental ways. Within the Indian Ocean, the Java Trench introduces a different dimension of understanding, showing that the seafloor is not only a place of accumulation and growth, but also of return, where material moves back into the depths from which it once emerged. On a morning in late December, the boundary beneath the eastern Indian Ocean shifted in a way that had been building quietly for a long time. Along the section of the Sunda system near Sumatra, two plates that had been moving against one another did not slide smoothly. Instead, strain accumulated over years, held in place by friction along the fault until it was released in a sudden and powerful adjustment. When this release occurred in 2004, the movement extended across a vast portion of the seafloor. The rupture propagated along the boundary, displacing sections of the crust and altering their position by several meters in places. This change did not happen at the surface, but deep beneath the water, where the interaction between plates had been storing energy over an extended period. The shift affected not only the immediate region of the fault, but also the shape of the seabed above it. As the crust moved, parts of the ocean floor were lifted, while others settled, creating a vertical displacement that transferred energy into the overlying water. This motion initiated a series of waves that traveled outward across the ocean, carrying the effects of the event far beyond its origin. Before this moment, the deeper parts of the Indian Ocean were often understood as distant and largely unchanging. The processes shaping them were recognized in scientific terms, yet their scale and impact were not widely experienced. The earthquake brought those processes into clearer focus, demonstrating that the seafloor is not a fixed foundation, but a dynamic boundary where forces continue to act. The evidence of this movement remains recorded in the structure of the ocean floor and in the data collected from the event. Measurements of the displacement, the pattern of the rupture, and the propagation of energy provide insight into how stress builds and is released along such boundaries. These observations contribute to a broader understanding of how tectonic systems operate over time. At the same time, the event underscored the connection between the deep ocean and the surface world. The motion that began along the fault translated into changes that reached coastlines across the region, linking a process beneath the seafloor to its effects far above. This connection highlights the continuity between different layers of the Earth system, where movement in one part can influence conditions in another. The setting in which this occurred is part of the same subduction system that shapes the trench nearby. The ongoing descent of one plate beneath another creates the conditions for both gradual motion and sudden release. Over long periods, stress accumulates as the plates interact, and when it exceeds the strength of the boundary, it is released in events such as this. Understanding this process provides a more complete view of the Indian Ocean's structure. It shows that beneath the calm appearance of the surface, there are regions where energy is continuously stored and redistributed. These areas are not isolated, but part of a larger system that governs the movement of the Earth's outer layer. The 2004 earthquake stands as an example of how these processes can become visible through their effects. It does not represent a departure from the normal behavior of the system, but a moment within it when accumulated energy was released and its consequences became widely observed. Within the broader context of the ocean, this event reinforces the idea that the seafloor is an active component of the planet, shaped by forces that operate over both long and sudden timescales, remaining present even when they are not directly seen. In certain regions of the Indian Ocean, understanding does not arrive as a single clear picture, but as layers that overlap and quietly reshape one another. What appears, at first glance, to be a continuous body of water reveals itself through patient observation as a place where many different processes share the same space without blending into simplicity. The seafloor below is not guided by one dominant pattern. Instead, it carries the imprint of spreading ridges, descending plates, scattered highlands, and wide fields of settled particles. Each of these features follows its own rhythm, yet they remain in constant proximity, influencing one another in ways that are not always immediately visible. A shift in one region can alter conditions in another, creating subtle chains of cause and effect that unfold over long intervals. This overlapping structure means that discoveries rarely belong to a single category. A vent field, for instance, is not only a geological formation, it is also a chemical system and a biological setting. A sediment deposit is not merely accumulated material. It records distant erosion, changing currents, and the slow passage of time. Even an isolated rise in the seafloor becomes more than a feature of rock, as it redirects movement in the surrounding water and offers structure where there would otherwise be none. Because these elements coexist, the Indian Ocean does not present its mysteries in isolation. Instead, they appear where different systems intersect. A chemical gradient may exist because of tectonic activity. A cluster of organisms may form where currents meet an unexpected obstacle. A hidden fragment of ancient crust may lie beneath younger layers shaped by volcanic processes. Each discovery carries traces of several influences at once, making it part of a larger, interconnected story. There is also a quiet unevenness in how much of this environment has been observed. Some areas have been studied in detail, while others remain known only through brief visits or indirect measurements. This uneven attention does not reflect a lack of interest, but the difficulty of reaching and examining such distant depths. As a result, knowledge accumulates in scattered patches, leaving broad regions where fundamental details are still emerging. When new information arrives from these less familiar places, it often carries a sense of suddenness. Features that have existed for immense spans of time appear in human awareness as recent findings. This does not mean they are newly formed, but that they are newly seen, revealed as the gaps between observations begin to narrow. The impression of surprise is shaped by this pattern, where long-standing realities come into view all at once. In this way, the Indian Ocean becomes a place where expectation must remain flexible. Patterns that hold in one region may not extend to another, and familiar explanations may need adjustment when applied to different conditions. The ocean does not resist understanding, yet it does not yield it quickly or uniformly. Across its depths, the meeting of geological motion, chemical exchange, and biological adaptation continues without pause. These processes do not wait to be observed. They unfold steadily, shaping environments that can differ greatly even within short distances. The result is a setting where discovery is not an occasional event, but an ongoing presence, built into the structure of the ocean itself, quietly waiting to be encountered. Long before any discovery reaches a page or a screen, it begins with a slow alignment of tools, timing, and intention. The search itself is careful, almost quiet, unfolding far from immediate view. Out on the open water, research vessels move across the surface, not as passing ships, but as deliberate platforms of observation, carrying instruments designed to extend human reach into places where direct presence is not possible. Beneath these vessels, sound becomes one of the first guides. Pulses travel downward, spreading across the unseen terrain, then return as faint echoes that must be translated into form. From these returning signals, contours begin to appear, not as images in the usual sense, but as measured variations that slowly assemble into maps. Each pass adds detail, refining outlines that were once uncertain until the shape of the seafloor emerges with increasing clarity. Yet mapping alone is only the beginning. To move closer, scientists rely on remotely operated vehicles, machines built to endure pressure, darkness, and distance. These vehicles descend along cables or navigate freely, carrying cameras, lights, and articulated arms. Their movement is steady and unhurried, guided from far above by operators who interpret delayed signals and subtle shifts in position. Every adjustment is small, each motion considered, as the vehicle approaches environments that have remained untouched by direct human contact. When the first images arrive, they do so gradually, line by line, frame by frame. Early transmissions can appear indistinct, shaped by low light and drifting particles, but with time, the scene stabilizes. Surfaces come into focus, textures reveal themselves, and structures that were once only suggested by sound begin to take visual form. The moment is not sudden. It unfolds through patience, as clarity replaces uncertainty. Sampling follows observation, and it is carried out with equal care. Mechanical arms extend, guided with precision, collecting fragments of rock, sediment, or fluid. Each sample is small, yet it carries within it a record of conditions that cannot be replicated elsewhere. Once brought to the surface, these materials are examined through techniques that reveal composition, age, and origin, adding layers of understanding that complement what was seen below. Imaging systems continue to refine this process. High-resolution cameras, sensitive to faint light, capture details that earlier expeditions could not record. Sensors measure temperature, chemical composition, and subtle variations in the surrounding environment. These instruments do not simply document what is present, they help trace how different elements interact, offering insight into processes that operate beyond immediate visibility. The first widely shared images from deep regions of the Indian Ocean emerged through this combination of mapping, descent, and observation. They were not the result of a single moment, but of repeated efforts, each building upon the last. Robotic systems made it possible to remain in place, to look closely, and to return with consistent data, transforming brief glimpses into sustained study. What becomes clear, over time, is that discovery here is not an act of sudden revelation, but a practice shaped by persistence. Progress is measured in incremental gains, in clearer images, more precise maps, and samples that extend understanding step by step. The process itself carries a rhythm, steady and deliberate, mirroring the environment it seeks to explore. Through these methods, the hidden parts of the ocean do not yield all at once. They emerge slowly, shaped by the tools that reach them and the patience that guides those tools. Each finding is part of a longer effort, one that continues to unfold with care, revealing a world that can only be known through sustained attention and quiet persistence. There is a quiet imbalance between the scale of the Indian Ocean and the portion of it that has been closely observed. Vast regions extend beyond the reach of detailed mapping, existing in a kind of measured absence, where outlines are known but finer structure remains indistinct. The surface is crossed often, yet the deeper layers beneath it hold far fewer traces of sustained attention. Much of what has been recorded comes from brief encounters rather than continuous presence. A survey line passes once, perhaps twice, leaving behind a narrow strip of clarity surrounded by broad areas that are still interpreted rather than directly seen. Instruments gather information in fragments, each fragment accurate in itself, yet separated from others by distance and time. When these pieces are brought together, they form a partial understanding, one that suggests patterns without fully confirming them. In coastal regions, the situation is different. Proximity allows for repeated observation, seasonal comparison, and the gradual refinement of knowledge. By contrast, the deeper reaches of the Indian Ocean remain difficult to revisit in the same way. The effort required to return to a specific location to maintain presence long enough for careful study is considerable. As a result, many findings stand alone without the context that repeated visits would provide. This uneven coverage shapes the way discovery unfolds. New observations can feel unexpectedly complete, not because they are fully understood, but because they arrive in areas where little was previously known. A single expedition may reveal structures, conditions, or communities that had not been documented before, giving the impression of sudden emergence. In reality, these features have been present all along, their visibility delayed by the limits of access and observation. The tools used to explore these depths continue to improve, extending the reach of measurement and imaging. Even so, the scale of the environment ensures that progress remains gradual. Each addition to the map, each collected sample, reduces uncertainty in one place while leaving many others unchanged. Knowledge expands, yet it does so unevenly, creating a landscape of understanding that is detailed in parts and sparse in others. Within this pattern, uncertainty becomes a natural part of the scientific process. Interpretations are formed with care, often held lightly, ready to be adjusted as new information arrives. Hypotheses connect isolated findings, offering explanations that may later be refined or replaced. The work proceeds without finality, shaped by the awareness that unseen regions still hold information that could alter what is currently understood. This balance between the known and the unknown gives the Indian Ocean a particular character. It is not defined only by what has been discovered, but also by the extent of what remains unobserved. The presence of unanswered questions is not a sign of absence, but of scale, reflecting an environment that exceeds the pace of exploration. In this setting, mystery is not confined to distant history. It persists alongside modern instruments and careful study woven into the process of discovery itself. Each measured advance reveals new detail while also outlining the limits of current knowledge. The ocean, in its depth and breadth, continues to hold more than can be seen at once, offering a quiet reminder that understanding is still unfolding, one careful observation at a time. A different kind of attention has begun to gather over the deep Indian Ocean, not sudden or dramatic, but steady, widening, and quietly deliberate. It arrives from many directions at once, carried by researchers, institutions, and careful observation, each contributing to a growing awareness that these depths are no longer distant in the way they once seemed. Part of this renewed focus comes from the expanding study of life in environments far removed from familiar conditions. Organisms that inhabit these regions are now examined not as isolated curiosities, but as parts of interconnected systems shaped by chemistry, pressure, and time. Their existence suggests that biological diversity extends into places once thought too extreme to sustain it, and this recognition has begun to draw sustained scientific interest toward areas that had previously received only brief attention. Geological inquiry has also deepened in parallel. Structures beneath the Indian Ocean are now considered not only as features to be mapped, but as records of processes that continue to shape the planet. Ridges, basins, and scattered elevations are studied for what they reveal about movement within the Earth, offering insights that connect the seafloor to broader planetary patterns. Each formation becomes part of a larger narrative, one that extends beyond location and into the dynamics of the planet itself. At the same time, the materials found within these environments have come into clearer focus. Mineral accumulations, formed over immense spans, are now part of discussions that extend beyond scientific curiosity. Their composition and distribution have drawn attention from groups interested in their potential use, bringing economic considerations into a space once defined primarily by exploration. This shift introduces a new layer of complexity, where knowledge and interest begin to overlap in ways that require careful thought. As these different strands converge, the nature of discovery begins to change. Identifying a new system or documenting an unfamiliar environment is no longer seen as a final achievement. Instead, it becomes an early step, one that leads into questions about how such places are understood, how they are approached, and how they are regarded within a broader context. Observation opens into consideration, and consideration carries with it a sense of ongoing responsibility. Hydrothermal regions, mineral fields, and elevated seafloor structures are now viewed through this expanded lens. They are not only sites of scientific importance, but also parts of a larger environment that must be approached with awareness of their complexity. The presence of life, the slow formation of materials, and the interconnected nature of these systems suggest that each location holds more than immediate value. It holds relationships that extend beyond what is first observed. This evolving perspective does not replace earlier approaches, but it adds to them, creating a more layered understanding of what it means to explore. The deep Indian Ocean is no longer seen solely as a place to uncover what is hidden. It is also a place where each finding invites reflection on how knowledge is used and how presence is maintained. In this way, interest in the region continues to grow, not as a single movement, but as a gradual alignment of curiosity, study, and careful consideration. The ocean remains vast and only partially known, yet the attention directed toward it carries a different weight now, shaped by the recognition that discovery is part of a longer process, one that extends beyond the moment of finding into the ways in which those findings are understood and carried forward. In certain parts of the Indian Ocean, knowledge arrives faster than understanding can follow, and this uneven pace creates a quiet tension beneath the surface of discovery. Some organisms that have only recently been observed appear to exist within narrow stretches of habitat, bound to conditions that do not extend far beyond their immediate surroundings. Their presence is precise, shaped by chemistry, temperature, and structure in ways that leave little room for movement beyond those boundaries. This limited range means that even small changes to their environment can carry significant consequences. A shift in chemical balance, a disturbance of the seafloor, or the introduction of external activity can alter conditions that these organisms rely on with exacting sensitivity. Because their distribution is so restricted, there are few alternative spaces into which they can move. Their existence is closely tied to the stability of the place they inhabit. Among the examples that have drawn attention, one particular species has come to represent this fragile balance. The scaly foot snail, found in certain hydrothermal regions of the Indian Ocean, lives within a confined setting where its survival is closely linked to the chemical environment around it. Its structure, reinforced by iron compounds, reflects the conditions in which it formed, while its internal symbiotic systems allow it to draw energy from processes that occur within its surroundings. Every aspect of its existence is shaped by the specific characteristics of its habitat. What makes this example especially significant is not only its uniqueness, but the narrowness of its distribution. Known populations occupy limited areas, making them particularly sensitive to disruption. As interest in the materials of the deep ocean has grown, these habitats have entered conversations that extend beyond observation into potential use. The same regions that support rare forms of life may also contain resources that attract extraction efforts. This overlap introduces a delicate situation. The act of studying these environments has brought them into clearer view, yet that clarity also places them within reach of activities that could alter them before their full complexity is understood. Scientific knowledge, still developing, exists alongside decisions that may affect the very systems it seeks to describe. The timeline of discovery does not always align with the timeline of action. Within this context, the meaning of finding something new begins to shift. It is no longer only about revealing what was hidden, but also about recognizing the conditions that allow it to exist. Each observation carries with it an awareness of how easily those conditions could change. The presence of rare organisms becomes part of a broader consideration, one that includes not only curiosity, but care. The Indian Ocean, with its many overlapping systems, holds environments that have remained stable over long periods, shaped by processes that operate slowly and precisely. When these environments are disturbed, the effects may not be immediately visible, yet they can extend through systems that depend on balance and continuity. Recovery, if it occurs, may take spans of time far beyond immediate observation. In this way, discovery introduces a quiet responsibility. The more clearly these environments are seen, the more evident their vulnerability becomes. Knowledge brings detail, and detail reveals limits, showing how finely tuned many of these systems are. As the deep Indian Ocean continues to be explored, its hidden life does not only expand understanding, it also invites a more careful presence, one that acknowledges that some parts of this world may be altered before they are fully known, and that the act of seeing them carries with it a lasting weight. There is a point, late in any long observation, when the pieces begin to settle without fully closing the picture. The Indian Ocean, traced through careful study and quiet descent, offers such a moment where what has been revealed does not form an ending, but a widening horizon. Across its depths, patterns have emerged that were once only hinted at. Heat moves through fractures in the earth, shaping environments where chemistry becomes a source of energy. Structures rise and fall across the seafloor, forming landscapes that remain unseen from above. Beneath layers of younger material, fragments of far older crust persist, carrying the memory of a planet that has shifted and reshaped itself over spans that extend beyond ordinary measure. Elsewhere, wide fields of sediment have gathered slowly, grain by grain, recording the passage of distant rivers and the steady work of currents. Subtle chemical processes leave traces within these deposits, preserving changes that unfolded long before they were observed. Even the quietest regions, those that seem still at first encounter, hold evidence of motion, accumulation, and transformation that continues without pause. Life has taken form within these varied settings, not as an exception, but as a response to the conditions that exist there. Organisms have adapted to environments where familiar sources of energy are absent. drawing instead from processes that operate beneath the surface of the seafloor. Their presence reflects a broader truth that living systems can emerge wherever stable conditions allow, even when those conditions differ greatly from what is commonly expected. These discoveries do not feel unusual because they belong to imagination. They feel unusual because they reveal aspects of reality that lie outside everyday experience. The deeper the observation, the more apparent it becomes that the boundaries of the familiar are narrow and that much of the planet operates according to patterns that are only gradually coming into view. At the same time, what has been learned remains incomplete. The mapped regions, the sampled sites, and the recorded images form a growing body of knowledge, yet they exist within a much larger context that has not been fully explored. Large areas remain defined by inference rather than direct observation, and many processes continue to be understood only in part. Each answer, when it arrives, often leads quietly to further questions that extend beyond it. This ongoing process does not diminish what has been discovered. Instead, it places those discoveries within a broader frame, where knowledge is seen as something that develops over time, shaped by repeated observation and careful interpretation. The Indian Ocean does not present itself all at once. It reveals itself in stages, each one adding depth without removing uncertainty. In this sense, the ocean floor beneath it remains unfinished, not because it lacks form, but because understanding has not yet reached its limits. The planet continues to move, to reshape, and to create conditions that evolve slowly across immense spans. What is observed today is part of that larger continuity, a moment within processes that extend far beyond it. As the descent of observation continues, the impression that remains is not one of completion, but of quiet expansion. The deeper science looks, the more the Earth appears not as a fixed surface, but as an active and ancient system, still forming, still changing, and still holding within it layers of knowledge that have yet to be brought into view.